Good morning, everyone. My name is Jennifer Wang. I'm the faculty at the radiology department. I'm also the co-chair of this M Alliance. It's my honor to introduce Dr. Shih as our keynote speaker this morning. Dr. Shih is a professor and vice chair of informatics in the Department of Radiology at Cornell Medicine. He went to medical school at Duke University and completed his radiology residency and fellowship training at Columbia University. His background is in radiology, machine learning, computer science, and electrical engineering. Dr. Shih holds a lot of important positions in medical AI field. Some of his current positions include RSNA Informatical Committee, RSNA Machine Learning Steering Committee, and RSNA Machine Learning Data Standards Committee. He's also the co-chair for same Machine Learning Committee and the Society of Abdominal Radiology AI Committee. He's also on the editorial board for the Journal of Digital Imaging, and he's the associate editor for Radiology Artificial Intelligence Journal. So other than the academic positions, Dr. Yi is also a co-founder of MD which is an AI startup trying to build a cloud platform for doctors, researchers, and engineers to annotate and create, validate, and deploy the medical AI. With that, I'm going to hand this podium to Dr. Xi. Welcome, Dr. Xi.
Hey everyone, can you guys hear me? Is Zoom okay? I can't tell if the Zoom people are okay. So thanks Jennifer and Jeff for the intro. My name is George Shih. I am a radiologist from Weill Cornell in New York City. I wanted to thank Stephen Hobbs, who's a radiologist, chest radiologist, Cody Baumgardner, Jennifer Wang, of course, Dr. Oates, Dr. Jennings, and the rest of the AIM leadership for inviting me to speak at the first UK AI and Medicine Summit. We had a great dinner last night at Dudley's, and so very live discussion around AI and Elon Musk and lots of other topics. I don't really know the audience today, but it looks like we have a mix of School of Medicine, but maybe some computer science or engineering. I don't know if there are any students in the audience, but any students here? No, a few. Okay, great, awesome. So it's nice to give a talk in person. It's probably only my second or third talk since 2020, right? I was supposed to give a talk last week in Tokyo at the Japanese radiology meeting, but they still have a lot of hoops and hurdles around that, and so I ended up not going. So I was very happy to visit Kentucky, and I didn't realize Keeneland was in their spring session. Otherwise, I would have planned to stay a little bit longer. So now I got to figure out how to advance the slide. Just the button, the green button. Okay. Does that work? Oh, the big green button. There's two green buttons on here. All right. Here are my disclosures. I'm co-founder and advisor. Nothing relevant for today's talk. So some of you guys may not know, but my dad is a retired UK professor. He practiced radiology for 30 years. He ran the nuclear medicine division at the VA for many years. In fact, Google still thinks that he works here. I just looked it up a few days ago, although I can assure you that he's happily retired. So don't believe everything you see online. My parents still live close by off Alumni, right next to Dr. Emery Wilson. You guys remember him? He used to be the dean. My dad was really nervous before they moved there because he was gonna live next to his, big boss, right? But they've been pretty awesome neighbors, and so uh, Dr. Wilson is a great guy. I get to see him every year when I visit my parents. So just a little bit about me. Let me advance the slide here. So as you may have figured out, I grew up in Kentucky. I went to James Lane Allen Elementary School, Beaumont Junior High, Lafayette High School. Any Lafayette grads here? No. I also spent a lot of my summers at UK when I was in high school. My first programming class was at UK. We were on the Radio Shack TRS-80s. I don't know if anyone took that class. My first hospital experience was at UK, volunteering in Dr. Vernon's in vitro fertilization lab. So UK really jump-started my education and career, both in radiology and AI. I then went to Duke University, studied computer science, ended up at Duke Medical School, and then after med school, I did residency in New York City at Columbia for radiology, and I've been working at Cornell ever since. Great. So today's topic is about AI bias and fairness, and I think for those of you guys interested in AI, it's a very important topic that hopefully you guys are becoming aware of. I wanted to start with this headline from a news story that I saw. This unfortunate gentleman spent 10 days in jail after facial recognition software led to the arrest of the wrong person. And this is one of the potential risks of AI, right? To a computer, these two pictures look like the same person, although to a human being, it might be easier to figure out that these aren't the same people, right? So I wanted to show you this New York Times headline, which asks, who is making sure that the AI machines aren't racist? And so in the audience today, some of you guys are in medicine or computer science. I don't know if there's anyone from industry, but hopefully the responsibility of this is, all of us together, right? Because AI is everywhere now, right? Just a few years ago, I don't think we could say the same thing, but we've really come a long way in terms of AI developments. And we see AI in areas such as education, employment, advertising, policing, healthcare, of course, right? Any other area that you guys can think of? Probably others, but since I'm visiting Kentucky, even horse racing, right? I had to throw that in, right? You knew that was coming from Kentucky. And here's a company that claims to predict the success of racehorses using just images. To me, that sounds harder than radiology AI. And I wonder if any of the horses running at Keeneland this week have benefited from this kind of AI. I didn't really look into it, but hopefully this is one of the companies that came out of UK. Or if not, I'm sure you guys could start one and do pretty well given all the equine research that happens here. So AI is everywhere. There's lots of cool AI, but is it fair and unbiased? And so this is a paper put out by a lot of the thought leaders in radiology, talking about the ethics of AI in radiology. And it says the things that you would expect, right? AI should be transparent, dependable. It should minimize harm and bias. And so there are lots of us thinking about this topic. But the question is, how hard is this? And what is the scope of the problem? And so I want you guys to think about this question, which is really kind of the topic of my talk. Is AI inherently racist, sexist, biased, or unfair? And before I get to that, I want to start by talking about banana sandwiches. So this is my favorite project from 2020. And the author is a machine learning engineer who had a lot of extra time on his hands because of COVID lockdown, right? He lives in New York City. It's very expensive, so he eats a lot of sandwiches. And so he decided to create some AI to help him make banana sandwiches. And the way that it works is that you take a photo of a banana and two slices of bread, and it predicts the best way to slice your banana and also where to put each slice on the bread to make the perfect banana sandwich, right? And so around this time, I was invited to give a talk uh, at another medical institution for grand rounds, and I was talking about this topic. So I said to myself, well, why don't I run my own banana AI experiments, right? And so I decided to run George's banana AI bias experiments. So the question I had was, will banana AI exhibit bias against different kinds of bananas, kind of more common and less common? So I want you guys to think about this, and maybe you can, vote ahead of time or just think to yourself. I'll come back to this at the end, um, but uh, but I thought this was going to be a lot of fun. Okay, so some of you guys have taken AI courses already. I'm sure there are great courses at UK. I mean, some of the more popular ones are online are the Stanford courses 231 and 224, I think, are the computer vision and NLP classes. Fast AI is very popular. And in those courses, there's a lot of math equations, right? And so you might be thinking to yourself, isn't AI more about math equations than skin color? Like, what is the issue here, right? Um, and that's a pretty valid question. Uh, and it turns out, and this is one of the key slides, that AI is not fair or just by default, right? The current way by which we do AI training and validation and testing does not at all mean that we're creating fair, ethical AI. And so you've seen some of the diagrams on this slide here. And in fact, we probably don't really even have a good way to test for fairness, right? Like I can run Banana AI and I can run a bunch of tests to see how it works on different kinds of bananas. But in the medical world, especially when we're doing research or even commercial applications, the way that we de-identify data strips out a lot of the important identifiers so that it's very difficult to test for the kind of fairness that we want. Part of it is because we're focused on privacy, but nonetheless, this is not obvious for us. Another potential concern, our current medical AI data set's big enough. We know from experience in the computer science literature that the bigger the neural network, the more data you have, the better the AI, right? And so most of us are working at an institution, a single institution, have access to that institution's data, but really is that going to be enough? And so how do we get access to more data? Um, uh, And so, how do we make AI more fair? At least in terms of radiology, I understand not all of you guys are from radiology, but at least in radiology, we need to consider minority populations, which is really what people are thinking about when they're thinking about AI bias and fairness, right? You want to worry about the minority populations. But in medicine, we also have to worry about minority diseases or diseases that are not very common, and even minority presentation of diseases. So diseases that present in different ways. And sometimes they're all kind of linked together, right? A lot of minorities get different diseases and they present differently. So these are all kind of the issues that we need to think about. Uh, and and we know this is true, right? So this is an example. This is a slide from one of my colleagues where we know that African Americans are twice as likely than whites to die of prostate cancer. We know this is true for breast cancer. They have kind of a younger age distribution, higher, more severe disease essentially, right, than whites. So we see example after example of this. And so if we're creating AI for these diseases, we need to be aware of that. Next, I want to show you some examples of AI bias. I want to start with this quote that I like. A predictive policing system doesn't predict crime, it predicts policing, right? And basically what that says is if your training data is biased to begin with, your AI is obviously going to be biased, right? And unfortunately, we see example after example of this, study after study, where we we see, both racial and gender bias in the systems and applications that we use today. This is an example of a facial recognition software from 3 different companies, large companies, and they perform less well in dark-skinned females and just females in general, frankly. So AI is currently racist and sexist. We see this in the criminal justice system, where they use computer algorithms to determine who should receive parole. And unfortunately, in this example, this resulted in bias against blacks, where the recidivism prediction produced much higher false positive rates for blacks than for whites. We see this in the job or hiring market, where certain job platforms will rank candidates. In this particular example, it was ranking less qualified male candidates higher than more qualified female candidates. And we see this in some of our most commonly used apps like Google Translate. Is there any Hungarian speakers in the audience? No. Because I don't speak Hungarian, but in this example, Hungarian's on the left. You can tell that it uses a gender-neutral pronoun, right? So the pronoun has no gender. But on the right, you can see that it translates to he is the boss, she is the assistant, he is the doctor, and she is the assistant, right? And so Google Translate, in its current state, exhibits bias and sexism. And there was one researcher, Amanda Lewandowski, who was trying to figure this out. And she published a paper on how copyright law may be affecting bias. And I want to kind of talk about it briefly. In the paper, she talks about the word-to-vec algorithm. So this is a popular natural language processing algorithm that a lot of you guys probably have heard about. It was created by Google. And the way Google created the algorithm was that it licensed a big corpus of news articles from all the media organizations, and it trained all these word vectors. And because there was a lot of sexist content in these articles, the word vectors were sexist. Now, the problem is not that the word vectors are sexist, it's that no one has access to the training data, except for Google, right, to kind of fix these issues, so no one can remove the sexist content or add more neutral content. And I like this example in terms of copyright, because I think we have something similar in medicine in terms of the rules and regulations around being able to use and access data. I think it's very hard to get access to that kind of data. And so we might experience similar issues. Any NLP experts in the audience? No? Okay. So, Word2Vec is a few years old now. And so the latest and greatest GPT-3, right, was kind of trained on the whole internet, also exhibits the same kind of bias that you would expect, because just a lot of content out there that's biased. So those examples are outside of healthcare. Unfortunately, we also see bias in kind of machine learning algorithms within healthcare. This is an example where a big company was using an algorithm to figure out who should be in certain preventative care programs, and AI was less likely to refer blacks than whites who were equally sick to these programs, right? And so we see it industry after industry. And what I'm really concerned about is that the current AI that we're making and building may or may not exhibit bias already. We just have no idea whether it does, because we're not really paying attention to this, right? And I'll kind of go over how it evolved this way, and talk about kind of inherently how big data is unfair. And so the news doesn't get any better, unfortunately. Okay, so this is a chart of publications from the computer science literature on fairness. So computer researchers who are figuring out whether or not these machine learning algorithms are fair or not. And so you can see for the first few years, very few articles were published on fairness. In 2016, it was, oh crap, we need to think about fairness, right? And so where do you think we are in medical AI in terms of fairness? Thinking about fairness. We're probably in the LOL stage, right? Like we're not even barely thinking about this, right? Um, okay. Uh, and if we take a step back, let's think about how machine learning, learns from data, right? In the case of deep learning or neural networks, we can think of training data essentially as historical instances. And the machine learning algorithm will pick up statistical patterns in the training data, including potential biases against minorities. Even when the race and the gender and the other protected attributes are not explicit in the data. So if you think about looking at a bunch of chest X-rays or CT scans, a lot of times you can tell if it's a male or a female by looking at the images, right? And patient gender might seem more obvious than race, but we're starting to realize that even patterns of race may be inferred by machine learning. This is a paper published last year by a friend of mine, Aman Banerjee, who's now at the Mayo Clinic, where she and her team were able to recognize the patient's racial identity in radiology images, which is pretty scary and fantastic at the same time, right? And just to show you that inherent in our data is all these encodings uh, of these protected classes. And so in the United States, we have anti-discrimination laws that protect certain classes, and I've listed them here, right? So things like race, sex, religion, age, family status, etc., are all protected by our laws. And it means that you cannot discriminate based on any of these statuses. It means that the AI that we create can't perform much worse for any of these statuses. Otherwise, you're discriminating. And so for protected attributes like race and gender, we just saw that they're typically redundantly encoded in the features of the machine learning models, even if we don't know kind of on the screen that this is a man or a woman, you can just tell from the image. And when these attributes are correlated with a particular algorithm, this is exactly what we'd expect. This is the whole appeal of machine learning, right? The problem is that there's no way to tell which correlation is worrisome or is discriminating or biased or unfair, and in which cases it's fine to have these correlations. So this is really the hard part here. And I know I talked about data set size, but data set size may not matter because even with unbiased training data, machine learning can still be unfair because by definition, there's always going to be less data about minorities. So the machine learning models that you create will always perform worse on minorities than compared with the general population. So these automated decisions tend to favor the dominant groups. There are all these other kind of issues and complexity, right? Maybe you're thinking, well, you have a AI algorithm works really well for the majority population. Why don't we make a separate algorithm for the minority population? But this requires that you test and act on these protected attributes, right? And that may be against the law. You're not really supposed to have two different ways of treating people, right? And so it's actually really hard to do something like that. Also, achieving fairness might be computationally expensive. This is a very important point for all the academics in the audience because it's very hard and expensive to get all the GPUs that you might need to train these more complicated algorithms. And if you're going to incorporate kind of these issues around bias, the final algorithm might be more complicated, so you would need more GPU compute. It's going to be really hard for us to compete against companies with unlimited resources. And finally, the definition of minority is fuzzy. There could be many overlapping minority groups, no straightforward way to determine which group a particular person in. For example, what minority group is Kamala Harrison, our vice president? What about Emma Raducanu? Emma Raducanu is the kind of last year's U.S. Open winner, and she was born in Canada, lives in Great Britain, has a Chinese mom and a Romanian dad. Like, which group is she in? Right. By the way, we went to the U.S. Open final. This is in the bottom corner there is a photo, a selfie of my daughter and Emma together. And let's say you trained an algorithm, and the algorithm, the model achieves 95% accuracy, right? I want to talk about what that potentially means. So noise and the meaning of the 5% error. Few models actually are 95% accurate. And if you're training a clinical AI model that's 95% accurate, the first thing you would probably do is celebrate, and kind of be really excited about this. But so this is very unusual. But even if we get lucky, we get 5% error. We typically have no idea what that error means. Is it just intrinsic uncertainty? Because AI is never going to be perfect. It's always going to make some mistakes, right? I mean, you hope it doesn't make too many mistakes, but it's never going to be 100%. So is it intrinsic uncertainty, or is it that it's 50% inaccurate for minorities and 100% accurate for the majority population, right? So which is it? Is it low accuracy for minorities, even if overall it's very accurate? So this requires a great deal of domain expertise to unravel, and I think it's a really nice opportunity for the clinical folks who are helping out with these AI projects. It's not easy to figure this out. Here are some examples of bias. I'm not going to talk about this. I'm sure a computer science professor would do much better than myself in explaining this. I do want to touch on fairness and how our anti-discrimination laws evaluate fairness. Does anyone know what ENL means? No? No kids in the audience? I have to learn all these like new abbreviations because of my kids, right? So it means I am not a lawyer, right? So that's my disclosure. I am not a lawyer, but I'm going to attempt to describe our anti-discrimination laws. So in the US, we look for discrimination in two ways, either disparate treatment or disparate impact. So the way I like to think about it is that you look to see if there's equal opportunity and you look to see if there's equal outcome. And if there's not equal opportunity or if there's not equal outcome, then potentially the medical AI algorithm that you're using is biased and discriminating, right, against a particular population. So that's how our laws describe it. The problem is that this is too abstract for the purposes of computation, right? So you can't compute on these laws, right? And unfortunately, there's no consensus on the mathematical formulation of fairness. And this is what everyone is rushing to solve, right? In fact, if you look at the computer science literature, there are no less than 21 fairness definitions. So you can tell that a lot of people think fairness should be computed in different ways. There's some proposed fairness metrics that I've listed here, things like demographic parity, equal opportunity, predictive rate parity, and the list goes on and on. And these are, great metrics for certain things like bank loans, right? So who should get a bank loan? Well, maybe you can use demographic parity and see if there's equal acceptance rates of, minorities and non-minorities for bank loans. But that doesn't necessarily mean that these are great metrics, fairness metrics for medicine. So what about fairness metrics in medicine? I think it's kind of an open question right now, but I do want to give an example in another area of healthcare in de-identification. So when we create our medical AI data sets, especially for research, we have to de-identify them in a way that doesn't reveal any PHI. And there are many ways to do this, but there's a concept of k-anonymity, which essentially allows you uh, to kind of dial the knob, if you will, between data utility and privacy, like the amount of PHI you identify. You can apply this k-anonymity because there's always a trade-off between data privacy and utility, right? And so if you want more privacy, you can get that. If you want more utility, you can get that. But it's a very useful thing to think about. And um, what I actually think that we need, and I'm totally making this up because this doesn't exist, right? Is that we need a concept that's similar, maybe called K-fairness, where we could just say, hey, we need K percentage of patients to be from minority groups. And if we have that, then we know that the medical AI that we're going to create will be fair, right? Um, so it definitely needs more work. Great. So what are some of the solutions? Um, and this is kind of my summary slide. AI is not fair or just, right, by default. And so, um, wow, everything is number one, huh? This got copied over from Google Slides. So clearly the export function doesn't work perfectly. So number one, we need bigger, better compute infrastructure, right, to be able to compete kind of with all the big companies. We need to think about minority populations, minority diseases, and minority presentations of diseases. Number one again, collect and select data differently, right? So we probably need to start including some of the protected attributes like race so that we can test against them. We need bigger, more diverse data sets. There may be a role for synthetic or fake data to augment kind of data that we currently have. And finally, we need to come up with better fairness metrics that apply to medicine and medical machine learning. And great. So now I want to go over the results of my banana AI experiments. I'm sure you guys have been, dying to see these results, right? Anyone want to guess ahead of time? Any votes for the yellow banana? Oh, sorry. So the question is, will banana AI exhibit bias against the darker banana, right? The less common banana, right? Um, Well, if it doesn't work, right? Like if it just breaks down, right? Like you remember the example was it like slice the banana and then it would put the slices on the bread, right? So is it going to perform on the darker banana the same way? Uh, Anyone vote for no AI bias? Just one. Just one? Wow. Two. Everyone else thinks it's going to be biased? All right. So this is the kind of thing that's nice about non-medical data because you can just run the experiments. I went to the grocery store, I bought a bunch of bananas, right? Took photos and I ran the AI, but you can't do that in medicine, right? Way, way harder, right? All right. So for you computer science guys, right, this runs in Ubuntu. This is how I installed it. You don't have to read it. I followed the instructions from his blog post, but it didn't work. So I had to like figure it out. The command line tool, right? So you kind of run it, it generates the image, right? And did a warm up with a yellow banana. So this is my banana, my bread, right? Works perfectly. Right? I try to trick the AI and I flip the banana, but unfortunately I put the bread too close together, so it thought it was one slice of bread instead of two. I'll go back and I'll show you guys. I'll go back. You see how the bread, look, just pay attention to the bread. I kind of moved it up, right? So you got to be careful how you position your bread, right? I tried another banana. It worked really well, right? And so for la pièce de résistance, like, what do you guys think? Right. So it worked perfectly fine. Right. So banana AI passes my AI fairness test. Great. Thank you guys. In the beginning of my slide, I put a QR code up for my slides. I don't know why it's not here, um, but you guys can have access to them. We can send out an email with a link. I think I'm supposed to talk about AI infrastructure. Is that right, Jennifer? Okay. Before I do that, I want to give a plug for the RSNA AI certificate. RSNAs are a big radiology society. The annual meeting's like the biggest meeting in the world, right? It's like 60,000 people. And we just put together an AI certificate. I'm one of the course directors, where it's teaching kind of radiologists kind of relevant AI content. It may actually be useful for non-radiologists as well. The goal is not to mimic, the other, 1,000 online courses for AI. It's to really give a focus on, how in medicine we think about these AI problems. So you guys can check out the website if you're interested. The other society that I'm involved in is called SIM. And so for the computer science people, you guys might be interested in this. It's a smaller organization, and every year they have an annual meeting. But what we did last year is that we had instead of a call for abstracts, we had a call for AI models, right? And so people, like you read an abstract and it tells you, I did this and it was 90 blah 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 percent accurate, and you know, and it sounds really good on paper, but what you really want to know is, does it actually work, right? So what we're asking people is to submit their models, and then we'll test it against different data, and then the outputs we're going to have, radiologists review and see if it passes their clinical test, right? I think this is the future of evaluating AI models. So we just decided, I was at a board meeting for SIM a couple weeks ago in California. We decided to launch this kind of year round. And so if you guys are interested in submitting your AI models, feel free to do that. I'm currently the co-chair of the machine learning committee for SIM. And then finally, a last plug, SIM is going to be in Kissimmee or Orlando, Florida this year. They roped me in to do a blockchain NFT learning lab. Has nothing to do with AI. If anyone's interested, feel free to join us. Great. Does anyone have any questions, or should I move on to kind of AI infrastructure? And how much time do I have left? I think I'm almost out of time, right? Okay. Any questions, comments before I move on? Okay. So they asked me to put together a few slides on AI infrastructure, very vaguely defined. So I'm just going to talk about a few things, and then we can have a discussion if you want. Okay, so AI infrastructure. So RSNA puts together a really great event every year. It's called Imaging AI in Practice. And so if you guys are interested in how AI will look like in the clinical world, it's a really nice exhibit to visit. I know not all of you guys go to RSNA. I think they have some YouTube videos as well. And so I've been part of that the last couple of years. And really, maybe what we'll visit first is some of the AI benefits. And this really is related to more radiology or clinical types of practices that look at images. And here I've listed some of the potential benefits of AI. Better care through prioritization, so things like triage, like which patient or which study should you look at first. The AI has kind of pre-detected some severe disease somewhere, right? So triage is a very big category or benefit. Second, reader checks, so having AI be a second reader. You can have more efficient processes through protocoling and scheduling. You can potentially automate very tedious tasks. And then you will have the ability to have better reporting capabilities, like transferring all the measurements into your report without having to type it in or dictate it in. So these are some of the purported benefits through AI. And this diagram shows you, it's a very complicated diagram, but it shows you kind of all the pieces or places in the current clinical workflow. And every single one of them is a potential opportunity to, incorporate AI or to improve the clinical workflow. There's also a post-imaging AI kind of integration or opportunities. So after you've, taken the X-ray, you've read it, you've dictated the report, the doctors who ordered the study has seen it and you've treated the patient, there's still other opportunities for AI to benefit in things like research, right? Also analytics that might improve your practice. So post-imaging AI. I made this list because I think this is kind of the main workflow. And I've highlighted the areas in red where I think it's the most important. This is where the money is, right? The triage, interpretation, reporting. And so having said that, in an academic practice like UK, I just wanted to say that there are kind of three areas to think about when you're kind of building AI at an academic place, right? The first one is in the clinical workflow, so that when a radiologist is reading studies, they want to leverage AI. You need the ability to deploy AI so that it's integrated into their clinical workflow. So really, clinical AI is kind of the first, AI infrastructure that you need to think about. The second area would be clinical research. Let's say you have researchers, like Dr. Wang, right, or like Cody, right, who are doing research, and they want a way to test out their AI in a clinical scenario, right? So in this case, you might have a separate infrastructure for this kind of AI, but it needs to be able to plug into the PAC system or the clinical workflow, right? So I put that separate. Sometimes the two categories, the first two can play nicely together, but not always. And then the third category is non-clinical AI research, right? Where, you're working on projects like, multimodal AI techniques, right? That no one's ever going to see, at least for the next 5 or 10 years, and MR pulse sequences, and that can be completely separate from the clinical workflows. And in those cases, researcher who has funding might have their own deep learning machines. Great. And then finally, I just wanted to talk a little bit about cloud versus local, in terms of where do you kind of put your infrastructure. We had a nice discussion over dinner last night, and we talked about how, Dr. Jenner, who I think is very involved in the UK healthcare IT committees, the IT committees at hospitals tend to be very conservative, right? And so IT tends to feel more comfortable if you're running all these AI models, and training data is stored locally within the UK ecosystem. So it's maybe easier to get started, right? Especially if you have some machines already. On the other hand, I find that it's harder to maintain, right? Especially from a security perspective. A lot of times it's a grad student who is maintaining the server, right? That contains millions of images, right? And that grad student is going to leave in like 3 years, right? And no one will know what the grad student did, right? It's just not a very, scalable way to run your AI infrastructure. It's also very hard to increase your storage and compute because you have to keep adding boxes, right? And so the cloud is the opposite of everything I just listed, right? It's much easier to maintain security. It's way, way easier to scale your compute and storage. It's almost infinite as far as we're concerned. right? And I think one of the big lessons from COVID that we learned was that, cloud is the big winner, right? Like if you were on the cloud, you were unaffected by lockdowns, right? So I personally think that everything is going to move to the cloud sooner or later. PACs eventually will all be cloud-based once some of the costs come down. It's still very, very expensive to do AI in the cloud, except if you're a big company. Great. So that's my kind of AI infrastructure. Thank you guys. Any questions or comments? Should we do questions now or wait for later? I don't know. Okay. Yeah.
Well, thank you, first of all, for coming and presenting. So I'm with the physical medicine rehab discipline. We're kind of just getting into like wearables and kinetics and kinematic data, and something I really want to see machine learning and deep learning kind of apply to. And I really appreciated your talk on like fairness, because that's something that's, like you said, kind of in an LOL stage. But then I think like on an institutional level, thinking like, what can we do to create fairness in, say, our training data? Because I think the training data is the important aspect. How do you make sure there's diversity in your training data? Is there anything like at your institution that you've seen done that's been helpful to diversify training data? I guess that's
right. Yeah. I mean, the first step, and I think this is true for a lot of issues, is to acknowledge the issue, right? And once you acknowledge it, you kind of like, it's the same for like, diversity of, people in the workforce, whatever. You're kind of more aware, so you're on the lookout for it. And I'm part of an organization that is collecting data from lots of institutions. And one of the things that we ask the contributing sites to do is to provide the demographics, right? These protected attributes, which I think is very different and unusual than what we currently do, right? And so unless you explain why you're doing this, the IRB is not going to be very happy potentially, right? And so I think that those are the discussions that you need to have on an institutional level. I think, in terms of collaborations, I think it's great if you guys can form collaborations with other institutions, either within Kentucky or kind of, nationwide, right? And I think it benefits everyone to have these collaborations. Another question.
Sorry, one quick follow-up question. The idea of interinstitutional like collaboration is, I think, would be enormous. And the challenges I see are like an institution might have their own cloud account with their own policies and protections. And then like you kind of touched on the conservative, right? There's some, do you want to share that with another institution? How do you navigate that? And I don't know if that's just a question or just a comment. I don't know if you've had any like navigating cloud storage across institutions. Has that been a challenge for you?
Yes, it's hard. It's hard to share anything, right? I think the first thing to do is just try it on a small scale, right? Like we've been sharing data for decades, right? Like all the cancer research, multi-institutional clinical, like this is not new, right? So there is a mechanism and a path of sharing data through the IRB. The main difference today is that we're talking about a ton of data, right? Before it was like a few cases a month or something like that. Now we're talking about, 10,000, 20,000, 100,000, and people are, very nervous about that, right? So start small is what I would do, right? Can you get an IRB approved for 100 studies, right? Also, there's some technology methods like federated learning that you can potentially use where you don't have to actually share the data, but you can still benefit and train machine learning through these using these methods. Okay. Thank you.
I'm sorry. We have a question from the chat.
Okay.
Oh.
So
Is federated federated learning an effective way to break silos to increase AI fairness, or is it
Yeah.
too complicated to deploy?
So that's a great question. I just kind of mentioned federated learning. I didn't get into the details, but uh, I have some friends that are working on federated learning, and it kind of requires that you don't move the data, you move the code to the different sites. The problem is that um, every site that you move your code to has to have the right computer hardware infrastructure. And so you're looking at kind of like some of the bigger academic sites that would have this, right? And in terms of the AI fairness and bias, a lot of the smaller institutions that may serve underserved populations wouldn't have a beefy GPU machine, right? In fact, you can't buy GPU anywhere now, right? So all the whatever the blockchain and Bitcoin is basically stolen all the GPUs. So the reality is that it's going to be very hard to do federated learning in the way that they've advertised it. I actually think it's fairly or more easier to do in the cloud. So I think we're going to see federated learning, but it's probably going to be in the cloud. Great. Thank you.
Okay, thank you very much for a great talk on a very complex issue related to the AI from your EMR system. I know that you mentioned last night you also use Epic. So recently we also switched to Epic, I think in the last June. So a lot of researchers just wonder, how can we get the data from the Epic? I don't know how you do it in Cornell. Can you share?
Yeah, sure. So in terms of data, so there are kind of two or a few different types of data, and it's different if you're in radiology and if you're not in radiology, in terms of the data that you care about. In terms of Epic data, what we do is I think we have a daily backup of the Epic database, and then we store that in our research environment. And there are probably a few different ones out there, but the one that we use is called I2B2, which is an open source way to store and query data for researchers. And if you have an IRB, you can access I2B2 and do very intricate queries for the kind of Epic data. We also have IT support to help you do that query if it's too hard for you, because some of the queries are very complicated. For radiology data, in our radiology department, we have a 3D lab. And so if you have a request to query images, all these queries go through our 3D lab. And this is an institutional policy, so they, and anyone outside of radiology would do the same. The main benefit of this is that our 3D lab is very good at this, and they can make large queries and de-identify the images kind of the right way, so that you're not worried about leaking PHI, right?
So it sounds like you already have a system or infrastructure established in your system to help researchers to get access to the data, and for example, from PAC system and Epic system. So
Yeah.
you already have that infrastructure and with very strong IT support for that.
Yeah, I think it works fairly well. I mean, nothing is perfect. We keep running out of storage. So we have a research PACS, right? And so lots of researchers pay us to, download their data and store their data. So we provide this as a service. It's not for free. The problem is that now the queries for machine learning are enormous, and so we keep filling up our hard drives. So eventually it's going to be impossible to expand the, you can't keep adding, the DASs, right? And so, so now we're looking to the cloud to store some of this research data. So like I said, I think eventually it's just going to move to the cloud, right?
Mhm. Thank you.
There was a question in the chat about where do you submit the radiology queries?
Oh, at UK or at Cornell? Oh, do we have something? So we go through the IRB, right? So let's say you want to do lung cancer detection and you want to get 5,000 CTs of the chest, right? Some with lung cancer. The first thing you have to do is write an IRB. And once that's approved, we have a query tool to look for lung cancer, which finds both positive and negative lung cancer. So we have some NLP so that you can find just the positive lung cancer, right? NLP is not perfect, so it misses a few, right? A few false positives. And then you also want a bunch without lung cancer. So you get a list of those studies. You send a spreadsheet to our 3D lab, and then they take that list and they have a program that just pulls the 5,000. So I don't know what UK does.
So, Dr. Shih, thanks so much for coming and appreciate your talk. And I think we're starting, at least in the research side, hopefully getting out of the lull phase of AI and bias. We certainly see a lot of funding from the NIH, or some funding from the NIH going into trying to address those things from a data set perspective. So I would say, if the question would be, if we had some way to develop unbiased AI that worked at the 95 plus percentile, and it was given to you free, so we could universally have it, what would you see as the biggest barriers for implementing that in clinical workflows across healthcare systems?
Right. Yeah. Yeah. It's similar to a little bit of what we discussed last night. I would say that there are probably two big barriers. One is just the integration of that AI into your clinical systems. Cody just said it was free, so you don't have to even pay for the AI, but there's still lots of costs in terms of IT work and support that you have to do to make it, perform well, so that the clinician or the radiologist, they don't have to do things that are very different from what they do today, right? The second big barrier, I think, is to change the habits of these doctors to be able to use and trust AI. I think that's a pretty big barrier. If you talk to the vendors from these AI companies, they're going to tell you we're deployed in 100 hospitals in the U.S. And then you go to one of the hospitals and you ask the doctors who uses this AI, and there's typically like 2 or 3 guys, right? And so the adoption kind of within the hospitals is not very high, I don't think, anecdotally, right? I think that will change over time. AI is going to get better. The residents who are coming up through training are going to be more adept. They're going to be used to AI. They're going to trust AI better. Hopefully, they'll be making their own AI, right? So over time, that problem's going to get better. But it's very hard to change physician habits, as you probably know.
Question from Zoom. Cloud computing is the future, but the current cost to maintain cloud storage for PHI is very high. Will this change in the near future? Or maybe do you think it will change in the near future?
So I don't work for AWS or Google Cloud, but I have friends that do. I think that everything gets cheaper over time, right? And that like everything else, it's eventually going to be more affordable. I'm not as worried about storage costs. Storage costs are actually pretty low already. I'm more worried about the compute costs. The compute for GPUs is still very, very expensive. So I think it's going to be very, very affordable in a few years, right? The problem is that if you have to wait a few years to start your research, you know, you're gonna be behind everyone else. And so, what do you do kind of until then? Great. Any other questions? I see Stephen Hobbs in the audience. I was gonna roast him earlier, but he wasn't here. So Stephen and I worked on a RSNA machine learning project together where we, or I should say Stephen, because I'm not a chest radiologist, helped to annotate and coordinated kind of lots of chest radiologists to annotate a data set, a CT of the chest data set for pulmonary embolism. That was publicly released. I think it was the biggest chest CT data set, right? Am I right, Stephen? And so I imagine that lots of AI companies will be using that data set to train their algorithms in the future. So if it ever misses a PE, you know who to blame, right? But this guy, he's responsible. The RSNA data sets? Oh, yeah. It's really geared for the average radiologist who is interested in AI but doesn't know where to start. So it may not be appropriate for everyone in the audience because I think what the average radiologist wants to know is kind of what is AI, right? How can AI help me? And then we go through the different steps of creating AI in radiology. And really, if you look at the development of radiology AI, there's only a tiny part that's computer programming, right? Most of the hard work is like figuring out what problem you want to solve, figuring out what the right data is, collecting the data, annotating the data, right? All the stuff that Stephen did for the chest CT data set, right? And then you have an annotated data set. Well, you just train it, right? Like that's the computer science part. But then after you train it, you got to test it. Is it good? Is it not good? Right? Like where does it break down? So all the steps before and after the programming are steps that the clinicians, the radiologists should be involved in. And so we kind of emphasize those parts. Yeah. Okay. Okay. Any other questions? So thank you guys. Thank you guys so much.